So last time we were talking about the epsilon-delta characterizations of limit and continuity. So I'll just remind you, here was the version of limit in R to the d in terms of epsilon-delta. All these things are a way of expressing that if x is near enough to the point A, that the function value f of x should be near enough to the value you're looking for. So this one is formalized this way, that for every positive real number epsilon, there should be, and this is allowed to depend on epsilon. As you make epsilon smaller, you're probably going to have to make delta smaller. For every positive real number epsilon, there corresponds some small positive real number delta, sufficiently small that as long as x is near enough to a but not equal to it, then the function value will be close to the value you want. Norm of f of x minus q will be small. That's for the function limit, and for continuity, you get the you don't need to worry about the x not being equal to a, because if x is equal to a, you're going to get f of x equal to the value you want anyway. So for continuity, because the value you're trying to get close to is actually equal to f of a, if x is equal to a, you're going to be exactly there, so you'll be less than epsilon anyway. So you don't have to worry about the not less than here. X is allowed to be equal to a now. And so as long as x is in your domain, of course, and close enough to a, then the function value should be close enough to f of a. Now, it's not as easy to use this formulation directly to prove some of the theory we've come up with, which is why we've been using sequences. Sequences are very good and clean when it comes to proving a lot of the theory, but aren't necessarily the easiest way to see what's really going on. And sometimes it's the epsilon-delta approach that gives you the quickest way to prove the result you want, which is what we get in the next lemma. So this lemma and variants of it are very useful in analysis. I'm going to make actually a couple of comments before we prove it, so I'll insert a couple of extra comments in a minute. But what does this lemma say? Suppose you've got a continuous function and you found a place where it's strictly positive. So it's a real valued continuous function. You found somewhere where it's strictly positive. And you want to know that it stays positive nearby. So what's going on here? That the idea is that if x is in your domain and near to a, then you want to make sure that f of x is still positive. Well, so let's have some comments first. First of all, what's continuity got to do with it? Let's have a different colour. Well, if you're not continuous, this result just isn't true. So the result is false without the continuity assumption. Let me draw you a sort of fairly typical discontinuous function from R to R and show you where things go wrong. Actually, you can't get away with just any old discontinuous function, but this one will work. So consider the following function, f from R to R, defined by f of x is equal to naught if, sorry, I don't want that. Well, it'll do, but let's be more extreme. Let's have minus 1 if x is less than 2, and 3 if x is greater or equal to 2. Let's have a look at what the graph of that function looks like. Notice that I've included 2 in the places where this function takes the values 3. Here's minus 1, here's 3, here's 2. So what have we got? Including this point here, which is in the graph of the curve, your 3 if x is greater or equal to 2. So here's y equals f of x. And this point here is excluded. And you come in along minus 1. All the way up to here. Sorry, I missed there. Let's try that again. So that point's excluded. So you're coming along minus 1. Until you hit 2, when you jump up to 3, and that's a typical discontinuous function. Now let's consider the case in the previous lemma where we take A to be the point 2 in the real line. So f of A is positive. So there you are. A is 2, so at that point, I've got f of A is 3. So it's positive. In fact, let me add that in. It's equal to 3. So you ask, does the lemma work? Do you stay positive if you stay near to the point x equals 2? Well, the answer is no, because if you're near 2 but to the left, you go negative straight away. So it doesn't matter which delta you try. So let's have a look at a little attempted delta here. None of them work, of course. So you look at 2 plus delta and 2 minus delta. And you ask, does a function stay positive in that little range? And the answer is no, because you can see that to the left of the point, it immediately goes below the axis. So can we find a delta greater than 0 such that f stays positive in the open interval with our alternative notation, 2 minus delta up to 2 plus delta, with our reverse square brackets? And the answer is no. And in fact, if you wanted to really tie it down, for any delta we try, note that one of the places you can find in that open interval is 2 minus a half delta. So if you really want to tie it down, it would be f of 2 minus a half of delta. That's definitely in that little open interval, but f of it is minus 1, which is smaller than 0. So if you've got a discontinuity like that one, you're in trouble. Just because you're positive at a point doesn't mean you stay positive near a point. And there's lots of variance on that. Any questions on that particular example? OK, if not, I want to move on to another little comment about real numbers that we'll use in the middle of the proof of this result. So here's a useful fact about the real numbers. Let x and y be in R, then the following are all equivalent. So these statements all mean exactly the same thing as each other. One is that mod x minus y, let me have an epsilon greater than naught as well. I'll have a delta, actually. I'll have an epsilon. Okay. Take some positive real number epsilon. The following things are all equivalent. Modulus of x minus y is less than epsilon. Obviously, I can change that to modulus of y minus x is less than epsilon. That doesn't change anything. So if one of these is true, all of the other ones are true. Carry on. That's the following statements are equivalent, by the way. Third one is that x is in the interval y minus epsilon, y plus epsilon. The fourth one is that y is in the interval x minus epsilon, x plus epsilon. So interestingly enough, you can think of that in terms of open balls. This generalizes to r to the d. If x is in the ball centered on y radius epsilon, then y is in the ball centered on x radius epsilon, and conversely. In particular, if mod x minus y is less than epsilon, then x is greater than y minus epsilon, and y is greater than x minus epsilon. Actually, that's another one that's equivalent, if you put both of those together. And we'll use that in the middle of this proof somewhere. So now we go back to the statement of this proof, which unfortunately is no longer on the screen, and I don't want to scroll all the way back to it. So you should look back at your statement of lemma 8.3.5, because we're going to prove that now. So what are we given? We're given f defined on this domain D, taking values in R, continuous, we're given a point A in your domain, and we're given that f of A is positive. Notice we're taking values in the real numbers. So D can have all sorts of vectors in it. So it doesn't make sense to talk about vectors being positive, but the function value here is a real number, so you can talk about that being positive. And we have to prove that some positive real number delta, so that when you're nearby, the function stays positive, as long as you stay inside D. So we're trying to show there exists a delta greater than naught such that for all x in the relevant ball, B delta of x intersected with D, we have f of x is greater than naught. Well, we know that the function is continuous, so we can use the epsilon-delta definition of continuous. We know that for every positive real number epsilon, we can find a small delta that guarantees that the function stays close nearby. So you could actually get away with epsilon equal to f of a, but I'm going to play it safe and take epsilon equal to f of a over 2, just to show you sometimes that would be a good idea. So that makes it even safer. So take epsilon equals f of x over 2, f of a over 2 which is positive, because we know f of a is positive. The epsilon delta definition says something is true for all epsilon. So we can take a particular value of epsilon and apply the definition there. So since it's true for all epsilon, it is in particular true for this epsilon. And we can find a delta. So by the epsilon delta definition of continuity, there exists a delta greater than naught such that for all x in that ball intersecting with D, which is exactly where we're going to be looking in a minute, we have modulus of f of x minus f of a. Remember, usually we would use norm, but because we're talking about real values, instead of using norm, we use modulus. That nearby, you'll be within epsilon. And remember, epsilon was chosen to be f of a over 2. We're going to check that this delta works. So then, for x in that intersection, we have f of x. By the comments we had before, if you're within epsilon, then you're going to be greater than the value minus epsilon. So f of x is greater than f of a minus epsilon, which is equal to f of a minus, but epsilon was a half of f of a, which is, again, f of a over 2, which is still positive. So actually, we did better than stay positive. We actually stayed at least half as big as f of a was throughout that open ball intersected with D. And so we finished. Nearby, you're still positive. Now, we saw an example that if you're discontinuous, that doesn't have to happen. So if we didn't use the fact that it was continuous anywhere in the proof, we must have cheated. But we did. We used it. We used the epsilon delta version of continuity in order to get the result. And that type of argument is where epsilon and delta come into their own. It's much harder to do that sort of thing using sequences. It can be done. Everything can be done with sequences, but it's artificial in this situation to do it with sequences. It's much better to just actually get your hands on what continuity means with epsilons and deltas. Right, so our next task then, before I move on again, any questions about that proof or the example before it? Okay, let's move on. So our task now is to look at what do continuous functions do to various kinds of sets, images under the functions. Now, I'll remind you what the image is. Recall correctly spelled. F of a set is equal to the set of all the things you can get to, f of x, where x is an element of A, the set of all the things you can get to from elements of that set A. So that's the image of the set A under the function f. And we want to know what sort of things can continuous functions do. And it turns out they can be quite bad. We're going to see in a minute that the continuous image of a closed set doesn't have to be closed. The continuous image of an open set doesn't have to be open. The continuous image of a bounded set doesn't have to be bounded. There's a rider on that one. But something funny happens when it comes to sequentially compact. The continuous image of a sequentially compact set is always sequentially compact. And because of all those other things I've mentioned about how badly wrong continuous images can go, this is actually rather surprising. Now, this bit of bookwork came up on the exam last year. And I'm very sorry to say that it was very badly done. In fact, I think about 90% of people got it wrong. So, but not only that, not only did it go wrong, it went wrong in a very revealing way, because people didn't do exactly what I asked them to do in the how do we do proofs sessions. So what went wrong when people gave this proof in the exam last year was that they didn't start the way they should start a proof for all sequences. They chose their sequences in the wrong place. In the middle of the proof, at some point in the proof, I will tell you where people went wrong. Oh, that was one of the ways people went wrong. The other way people went wrong was that they claimed that the continuous image of a closed set would be closed, which isn't true. And they claimed that the continuous image of a bounded set would be bounded, which isn't true. And then they said that means the continuous image of a closed and bounded set will be closed and bounded, which happens to be true, but not for the false reasons just specified. So putting all these things together, almost everybody got this proof wrong in the exam last year. So here's how you write it out in full then. The continuous image of a sequentially compact set is sequentially compact. So you've got some non-empty sequentially compact set, which is your domain. So your domain now is non-empty, sequentially compact, and you've got a continuous function defined on your sequentially compact domain, and you want to check that the image of D is sequentially compact. So let me set E to be equal to f of D. Now, if you want to prove that E is sequentially compact, using the definition of sequential compactness, you should now say, you have to prove that every sequence in E, and here's one of the optional extras, but it's a rather important optional extra. We must show that every sequence in E has a subsequence which converges to a point of E. Now, we know that D is sequentially compact, and we're trying to prove that E is sequentially compact. So what did people do in the exam last year? As I say, a very large number of people said, take a sequence in D. And some people said, take a sequence in D which converges. And some people said, take a sequence in D which has a convergent subsequence. And some people said, take a sequence in D, then we know it's got a convergent subsequence. But what almost nobody did, which should be almost automatic, is if you want to prove that every sequence in E does something, you should start with, let's take a sequence in E. Or suppose you have a sequence in E. So let me put a big ring around the fact we're trying to prove something about every sequence in E means that you should start the proof with, suppose you have a sequence in E. Should be almost automatic by now. So suppose that Yn is a sequence in E. OK, why did I use suppose? I can't remember if I insisted that it was non-empty or not. Hopefully I did. The empty set is always a problem, but I think if I said it was non-empty, then you can get away with let. So you have to start with that, and now we don't know that E is sequentially compact, because that's what we're trying to prove. So what can we use next? Not a lot, except that E is f of D. For each natural number n, since yn is in the image of D, we can find an xn in D so that f of xn is equal to yn. So now we've used the fact that E is the image of D. The nice thing about that is that now we have got a sequence in D. By the way, I've got quite a commentary on this in the comments on the exam performance last year. So if you want to see what I wrote there about what people did, it's pretty much what I've already just told you. Very well worth looking at, though. I always prefer it if people do look at the common errors from the previous year so that they aren't common errors if the same thing comes up again. If you look at the common errors from the previous few years, that'll help you avoid making common errors. Now we've got a sequence in D. So what could we do next? What do we know about D? Yes, D is sequentially compact. We didn't start with a sequence in D, but we've got one now. And since D is sequentially compact, this has got a convergent subsequence. So since D is sequentially compact, there are K1 natural numbers K1 smaller than K2 smaller than and so on, such that the sequence xkn, which runs from n equals 1 to infinity, converges, but it doesn't just converge. D sequentially compact means that you get a subsequence that converges to something in D. So such that that converges and the limit as n tends to infinity of xkn is in D. Well, what haven't we used so far that if we don't use it, we must have cheated? What have we got left to use from the assumptions? We've used almost everything mentioned in our assumptions, but one thing we haven't used yet. What's that? Anyone tell me? Yes, we haven't used the fact that's continuous. If we don't use that anywhere, then we must have cheated. So this is where we use that. Note that we got with the same kn as above, we've got this subsequence ykn. That's a subsequence of yn. And I'm going to claim that this is the subsequence we want that converges to some point of E, the image of D. So we claim ykn converges to a point of E, which is equal to f of D. And to see this is because ykn is actually equal to, remember, each y was the image of the corresponding x. Ykn is f of xkn. And xkn tends to sum x in D, say, by above. And then tends to infinity. So finally, since f is continuous, ykn equals f of xkn tends to f of x, which is, of course, in f of d, as required, and then tends to infinity. And we've finished. So let me summarize what we did. We wanted to prove something happened for every sequence in the image, E equals f of d. So we took a typical one. We took a prototype. We said, let ym be a sequence in the image. We used the fact that it was in the image to say that means there's some sequence in the original set whose images gave you that sequence. And then we were in good shape because we finally had a sequence xn in the sequentially compact set. But it took a while to get there. You can't start with that unless, if you do start with that, you're not following a standard proof structure, though you can fix it with care. Care that was unfortunately not shown by students in the exam last year. So you do need, I recommend following the standard proof structure and not trying to come up with a completely different proof structure of your own unless you're very, very careful. So we got to our sequence eventually, xn in the sequentially compact set. Then we took a convergent subsequence, which converged to something in D. Then we took the images back again, and we got a subsequence of the images, which was a subsequence of the original sequence we took, which again was converged to something in the image as required. And that proves that the image was sequentially compact, because it didn't matter which sequence you took in the image, some subsequence of it converged to something in the image. And that was it. So what goes wrong when you want to try continuous image of other kinds of sets being of that kind? Let me give you some examples. So, for example, here, consider U equals R, a subset of R. Okay, so working one dimension, and I'll take f from R to R, defined by f of x equals sine x. Then U is open. F is continuous. But f of U equals f of R. What do you get if you look at all the possible values taken by the sine function? What set do you get? Closed into a minus 1 to 1. Which I'll remind you, the fact that it's closed is not what we're after here, but the fact that it's not open is what we're looking for. It's got two non-interior points, one at each end. Right, what about continuous images of closed sets need not be closed? Let's take E equals R, a subset of R. It's a nice closed set. An example of a continuous f from R to R such that f of E or f of R is not closed why don't I give you a couple of minutes to think of one? So why don't you talk amongst yourselves for 2 minutes, just see if you can come up with a continuous function from R to R where, if you look at all the values taken by the function, what you get is not a closed set. Obviously, you can't use the one before. The one we just had, the image was the closed interval -1, 1, so you're going to have to do something different. So talk amongst yourselves for a couple of minutes and see what you can come up with. Okay, let's see what people came up with. I mentioned that there was a good try of x squared, but it doesn't quite work. Because you'd end up with a closed interval 0 to infinity. And it may not look closed, but unfortunately it is. So who came up with an example? Who thinks they've got one? Yeah, what have you got? Exponential function. Yes, that works. Then the image, f of R, the exponential takes you to all strictly positive real numbers. And that is not closed. There's lots of other things that do work and lots of other things that don't quite work. Any questions about those two examples? Now for the bounded sets one, it turns out there's a slight obstacle. You can't have a continuous function from R to R that takes a bounded set to an unbounded set. But if the function is only defined on the bounded set, then it can be okay. So let's go to the bounded set. So let's consider f from, I'll go from 0, 1 to R, defined by f of x equals 1 of x. That set 0, 1 is bounded, but so let's call that D. F of D swaps it over and you go from 1 up to infinity exclusive, and that's unbounded. So continuous images of open sets don't have to be open. Continuous images of closed sets don't have to be closed. Continuous images of bounded sets don't have to be bounded. But if you combine closed and bounded, you get this very strong condition of being sequentially compact, and that combination does get preserved by continuity. The continuous image of a closed and bounded set is closed and bounded. And so there's something unusual going on there, and that's why you need to think about all these issues and put them together. I think that's a good place to stop today.